Good evening, everyone, and welcome to this special ICTS Distinguished Lecture. The ICTS Distinguished Lecture is one of our flagship lectures, standalone lectures, which are delivered by eminent scientists in various disciplines. And we've had a very illustrious history of people delivering this set of talks. I think the first one was delivered by Ashok himself. It's now here, but we've had most recently people like Giorgio Parisi and David Gross, many others who have given these talks. So it's a particular pleasure to welcome today Professor Jainendra Jain to deliver today's ICTS Distinguished Lecture on a strange new universe where bizarre quantum particles rule. So it's a very proud moment for all of us in some sense that Jainendra has recently been recognized with the Wolf Prize in physics, which is one of the very distinguished, very sort of special honors for his work on the fractional quantum Hall effect and related matters, which he will tell us. Jainendra is an eminent theoretical physicist in the field of quantum condensed matter physics with interests in the area of strongly interacting electronic systems in low dimensions. He's best known for predicting a new class of particles that he has named composite fermions, and for explaining the phenomenon of the fractional quantum Hall effect as the integral quantum Hall effect for these composite fermions. And there are these special states and named after him for his contribution. He has been, other than the Wolf Prize as well, he's been recognized with a number of honors. He's a recipient of the Distinguished Alumnus Award of the Indian Institute of Technology, Kanpur, where he studied, the Oliver Buckley Prize of the American Physical Society, and of course the Wolf Prize I mentioned. He's a member of the US National Academy of Sciences, the American Academy of Arts and Sciences, and also a foreign fellow of the Indian National Science Academy. He has held visiting professorships at IISc Bangalore, TIFR Mumbai, IISER Pune, and hopefully we'll also see him more at ICTS in coming years. He currently holds the titles of Ivan Pugh University professor, I don't know if I pronounced it right, the Erwin Mueller Professor of Physics in the Eberle Family Chair of Physics at Penn State. I'd like to invite Jainendra to deliver his lecture. But before that, I'd just like to ask Professor Smriti Rao to come and hand over a little memento on behalf of ICTS to Jainendra.
Oh, thank you.
Has an ICTS sweatshirt and a mug. So
wonderful.
And the poster of your talk.
Thank you, Rajesh, for this very generous introduction. So Ashok Sen, Gross, Parisi, that's a hard act to follow. Kind of makes you nervous already. But what's that? So it's a string of letters, symbols, and numbers. And you say this is just a meaningless jumble of symbols, but it's not. It's actually an encoded message. Okay, so as soon as you know the encryption key, you can actually read the message. So theoretical physicists, they have different approaches to doing theory. they think about things differently. You know, that's kind of the beauty of the field. But to me, a theoretical physics is not that different from this. So often nature, Mother Nature provides us with a set of facts, you know, a collection of observations. And at first they may seem very mysterious, puzzling, and they may seem to have no connection at all. But the job of a theoretical physicist is to find the key, is to find the fundamental principle which certainly puts coherence over all those facts. And suddenly things become obvious. You know, you say, I understand. So that's something that happens all the time in physics. You know, this is the idea of unification. So lots of different things suddenly are explained by a single principle. But I will focus my talk on this system of two-dimensional electrons in a strong magnetic field. And we'll see in particular that a study of this, okay, I should stay on the other side. The study of this topic has taken us into a strange new world, which one would not believe if it did not exist. This strange new world has bizarre quantum particles, and in particular, the fundamental object that describes this new physics, I mean, this new world is called composite fermion, and we'll see that it is generated when electrons eat up some of the magnetic field. And then composite fermions give rise to other strange particles, for example, anions or Majorana particles. So all of these are, these particles cannot exist in three-dimensional world according to the laws of quantum mechanics. And even in 2 dimensions, as I said, one would not believe these particles existed, except that they do explain all of the physics there. So we'll see how that comes about. Okay, so this is, so, you know, Rajesh mentioned the Wolf Prize. So when my family learned about the news, they got a bit too excited. So they said, okay, let's have a celebration party. So they invited, this celebration party had some people from the physics department, but a lot of people, a lot of our friends who were not physicists. So, okay. Sorry, I need to, for some reason, I need to keep drinking water, so bear with me. So, my daughter, whose name is Saloni, you know, some of you know her. She is very methodical. So she asked ChatGPT, you know, she put in the question, okay, we are having a celebration for this particular purpose, and it will be a 3-hour-long thing. There would be dinner, there would be, and so on. So how should we best organize this? So ChatGPT suggested, okay, you should ask your dad also to give a 10-minute presentation explaining what all this fuss is about. So I thought about it. She said, you know, I thought about it. I said, how am I going to explain it to my non-physics friends? But then I remembered that a colleague of mine was showing me this book, Quantum Physics for Babies. I think all of the parents here may have seen it. You have, right? So there is a series of books, and you know, I have 2 beautiful granddaughters, so I bought a couple of these, you know, like Quantum Physics for Babies, Relativity for Babies, and so on. I gifted it to my daughter. She said, oh, we already have it. I've already read these to my kids. I said, okay, if we can explain quantum physics for babies, why can't I try at least to explain composite fermions to grown-ups who understand English at least? So I will try to keep, since then I've been trying to make things simpler and simpler. And in fact, it's kind of important for us to be able to say things in ways that our parents can understand. It's like the famous Feynman dictum where he said, if you cannot explain it to your grandmother, then you don't understand it, okay? So it's something we have to try, and I will make an attempt at this, although you guys are all physicists, so please excuse the simplicity here. Okay, so what I'll do is, so many of you have already heard this talk, or at least some version of this talk, but many of you haven't. So this talk is intended for someone who is not familiar with this field at all. I will tell you basically a story. So I'll go through go along the memory lane, tell you a story which has many twists and turns. So whenever we feel we understand something, something new comes up. And then you study it at some point, you feel you understand that something else new comes up. That's the nature of physics. So I will begin with the unfolding of the phenomenology of the fractional quantum Hall effect. What is the mystery here? I will then tell you and convince you that if you look at the problem just theoretically, it's an impossible problem to solve, okay? Then I will tell you that there is a key, there is an encryption key to this problem, which is these particles, composite fermions, depicted in this fashion here. I will say what motivated composite fermions and how it helps us explain the phenomenology of fractional quantum Hall effect. And then in the last 15 minutes or so, I will talk about some recent work, some really remarkable recent twists and possible future twists. Okay. So I assume you're all familiar with the Hall effect. So, okay, Ohm's law says that if we apply a current through a sample, then there is a voltage drop which is along the current path, and we can define a resistance. But what Edwin Hall discovered, and that was in 1979, so almost 150 years ago, that if there is also a magnetic field applied to the sample, I'm sorry? It should be 18. Okay, thank you. Yeah. So if there is also a magnetic field applied to the system, then there is also a potential drop across the current path. That's called the Hall voltage. And we can define a Hall resistance as given here. And simple classical electrodynamics can be used to derive the expression for Hall resistance as given by this equation here. B is the magnetic field, rho is the density of the charge carriers. So this says as a function of magnetic field, it has the straight line behavior, and the slope is related to the density of the charge carriers. So this is a law, this is a standard way to measure the charge, the density of the current carriers. And it's completely well tested, okay? So about 100 years later, the Hall effect was studied in two-dimensional systems. So these two-dimensional systems, you can now think of graphene. This is a two-dimensional system where electrons have only 2 degrees of freedom. But in the original experiment, they were using MOSFETs, which are there in all of our smartphones. So, all of these transistors are made of two-dimensional electron gases. You can also make quantum wells. You take semiconductors with different band gaps, put them together, and you can make quantum wells where electrons have only 2 degrees of freedom in their motion. So there are many ways to make two-dimensional electron systems. But the basic discovery here was, this was made by Klaus von Klitzing. So instead of this straight line behavior, he found that there are these regions, these are called plateaus, where the Hall resistance seems to be completely constant. Moreover, he discovered that the value of the Hall resistance on these plateaus is a universal value. So it does not depend on any details of the sample. You look at this expression, H and E are fundamental constants. I is an integer. It doesn't make any reference to the width of the sample, the length of the sample, which sample it is, what is the disorder. No, it's a completely universal number. And for all we know, this is exact. So you can take two different samples and ask how equal are the resistances on these plateaus, and they're equal to at least 12 significant figures. They're equal as accurately as you can measure the resistance. Okay, so moreover, if you look at the ordinary resistance, it's almost zero. So it's exponentially small. It goes to zero in the limit of temperature going to zero. This phenomenon is called the integer quantum Hall effect. So this is called the integer quantum Hall effect, and Klaus von Klitzing won the Nobel Prize for this in 1985. So what is happening here? Well, let's look at the problem quantum mechanically. So Landau had solved already the problem of a single electron in a magnetic field almost immediately as soon as quantum mechanics was discovered. And he found that in the presence of a magnetic field, the kinetic energy of an electron is quantized. So very naively, you can think of it this way. We know that in the presence of a magnetic field, electron goes around in a circle. And if you look at it quantum mechanically, then only certain orbits are allowed. Not all orbits are allowed. So therefore, the kinetic energy is quantized. Furthermore, Landau found, this quantum, so this is a pretty straightforward quantum mechanical problem. So how many of you have already solved this problem? Okay, so there are a few people. So this, if you know how to solve the problem of a harmonic oscillator, you can do this problem. So the number of spaces in each lambda level or degeneracy of each lambda level is given by this expression here, which tells us that where A is the area, this tells us that there is one state per lambda level per flux quantum, where flux quantum is defined in this fashion. Now, a quantity that would be of interest throughout this talk is called the filling factor. Okay. So another quantity of interest is called the filling factor. So it's basically how many lambda levels are full. In this example, the degeneracy of each lambda level is 3, and we have 2 1/3 lambda level full. Okay, so the filling factor is just total number of electrons divided by the number of available single particle states in each lambda level. Now, in general, the problem is the solution is not unique. So for example, here I could have put this electron here or here. But it turns out that for integer filling factors, we know the solution precisely. So let's just go over that. So let's switch off the interaction between electrons to begin with. Once we do that, as I said, for integer fillings, I know the solution. So I know I fill 1, 2, or 3 lambda levels exactly. It's a unique state. And I know the wave function of this state because that's just a Slater determinant made of these single particle states. And moreover, there is a gap to excitations because to create an excitation, I have to kick an electron into a higher lambda level. And these properties, a uniqueness combined with a gap, is what gives rise to integer quantum Hall effect. And I should say that now you can also switch. So you could ask, what about the interaction? Well, you can switch the interaction back on, And we know that at least perturbatively, the gap would survive. The gap gives some stability to perturbation theory. And unless the interaction is too strong, and so long as the gap survives, you see integer quantum Hall effect. Okay, so it's well understood, and the reason it's well understood is because it's a phenomenon that non-interacting electrons would show. Okay. So just to summarize, why do we see these plateaus? Because we have states of this form. So that's the explanation of the integer quantum Hall effect. So I was telling you about twists. So if we had stopped here, we would say, okay, that's a beautiful story, the surprising effect, nice explanation, we understand it. But just a couple of years, I should also mention that this integer can also be interpreted as a topological quantum number, and that was the a kind of starting point for a lot of this topological physics that you may have heard about. And for that, Haldane and Paulus won the Nobel Prize in 2016. Okay, just a couple of years later, Sui, Stormer, and Gassard went to yet higher magnetic fields, and they saw a plateau, except that now we have a fraction here, which is 1/3. And almost immediately, a theory for the ground state at this filling factor was written by Bob Laughlin. This is the wave function. And for this, 3 of these 4 gentlemen won the Nobel Prize in 1998. So again, you say, okay, that's a beautiful story. We see 1/3 effect. We understand it. We can write the wave function for it. But in this case, almost as Laughlin was, as his paper was coming out, more fractions began to be discovered. Okay, so in a few years, as the experimentalists improved the sample quality and experimental conditions, they started seeing states at with fraction 1/3, 2/5, 3/7, 4/9, and so on. Of course, whenever you see a plateau, you see a minimum here. So sometimes I won't show you, I'll show you only the ordinary resistance. And whenever you see a minimum, you should imagine that there is a plateau in the Hall resistance associated with that. And in a few more years, the data started looking like this. So I often make the claim, this is the most beautiful single trace in physics. This is just Hall resistance measured as a function of the magnetic field. And there's a tremendous amount of structure. At first, you might think this is noise, but it's not noise. All of this has meaning, and we will see that we can understand all of this detail. And there is rather beautiful physics underneath it. The fractional quantum Hall effect is actually among the most stunning manifestations of quantum mechanics at the macroscopic scale. And it's also one of the most striking mysteries that nature has presented us with. Okay. So remember in my first slide, I was saying there are lots of facts which at first seem unconnected. So what are the facts here? Well, you can count how many minima we have, and you end up with a number like 100 in the best samples. So there are 100 different fractional Hall states. They have different fractions associated with them. You can take any of these states, you can measure it in gallium arsenide quantum wells or graphene, measure its excitation gap. You can measure its transport coefficients like thermal Hall effect. So, and you can make a list of all of the properties of all of these states. You can produce lots of data. We theorists can also produce data actually. By putting some number of electrons, some finite number, which is not too small, So this is 18 electrons at some filling factor 3/7. We can get all eigenstates and eigenenergies by putting the system on the computer and doing exact diagonalization. Okay. So this has tremendous amount of information. So these are all the facts that I'm talking about. And so I had mentioned in the beginning that purely theoretically, it seems like it is an impossible problem to solve. And let me explain why I'm saying that. So let's write down the minimal model for fractional Hall effect. So at first you would say, okay, what does my Hamiltonian have? It has kinetic energy, interaction energy, Zeeman energy, and disorder. So let's simplify our lives by taking the limit where the magnetic field goes to infinity and there is no disorder. So this term I cross out, and it turns out that this term and this term, they are proportional to B, whereas the interaction term is proportional to square root of B. So we minimize this by putting all electrons in the lowest order level. We minimize this by assuming that they all have spin locked into in the favorable direction. And then these two terms become constant, which we can throw away. So by redefining units, we can write the minimal Hamiltonian in this rather simple form. It's Coulomb interaction. And the Hamiltonian is to be solved within the space of the lowest lambda level. Notice that there are no parameters in this model. There's, in particular, the electron mass is not a parameter. There is no kinetic energy in this problem. Okay, so what would we like to do? We would like to identify the fundamental principle underlying the fractional quantum Hall effects and to develop a microscopic theory that explains, unifies, predicts, and in addition enables parameter-free calculations. The expectation is that we would obtain unique gapped ground states at certain special fractional values of the filling factor, and these fractions would match with what the experiments are showing us. Let's do what we did in the integer Hall effect. So let's switch off the interaction to begin with. In fact, the minimal model, okay, so it has only interaction. So when we switch off the interaction, there's nothing left. We certainly don't get a unique gapped ground state because now there are more spaces in the lowest lambda level than we have electrons. So we can arrange the electrons in many different ways. We don't have a unique ground state. So we have to consider interactions. In fact, this is the most strongly correlated system in the world because often we describe the strength or we define the strength of correlations as the ratio of the interaction energy to kinetic energy. And here we only have current interaction energy. We don't have kinetic energy. Let me also say that there is no known exact solution to this problem, and I would bet that we will never find an exact solution to this problem. But, so some people might get very discouraged by this statement, but, for condensed matter physicists, that's not a big deal. Because even the problem of 3 interacting particles has no exact solution. So we deal with this all the time. We use perturbative methods to deal with problems, except that here, even perturbative schemes are useless because there is no small parameter. In fact, there is no parameter in this problem. Just to get a feel for things, let's ask, what are we dealing with? So if you take a baby system of 100 electrons at, let's say, filling factor 2/5, so that means 100 electrons in 250 spaces. And if you count all different ways of arranging these electrons, you get a number like 10 to the power 69. But if you take a system of billion electrons, which is the typical number of electrons in an experimental system, you have ridiculously large number of possible states, which are all equally good as far as theory is concerned. So this is not the case where we have to find a needle in a haystack. This is like we have to find a quark in the entire universe. Okay, because if you ask how many quarks are there in the entire universe, it's like 10 to the power 80. So these numbers are comparable to that. So if we don't even know where to begin, how are we ever going to find out what's happening? Okay, so this is a problem that we could not have solved but for the clues that experiments gave us. Okay. So, when we are students and we are studying physics, we are often given problems where the problem is given and then you figure out what the solution is. That's not the way research works. We don't know what the problem is. So problem has to be modified. The question has to be modified as we go on. In fact, I could say the question is more important than the answer. So the art of theoretical physics is to ask the right question at the right time. If the question is properly developed, refined, and sharpened, it often has the answer in it, or at least it points the way to the answer. So let's ask questions here. Okay, what question would you ask? So some examples could be, what's the physical origin of the fractional quantum Hall effect? What is the organizing principle? What's the mechanism? Well, these questions are not particularly illuminating. They're all asking what's happening. I mean, it's they don't point you toward anything. A more interesting question is, what are the weakly interacting emergent particles of the fractional quantum Hall effect? Now, at first, you might say, why do there have to be weakly interacting particles in fractional quantum Hall effect? I would say that it's actually a rule of nature that strongly interacting particles bind together to make weakly interacting particles. It happens at all scales. You take quarks, they combine into protons and neutrons. They combine into atoms. So you take some bunch of quarks and electrons, put them in a bucket, and you might end up with helium-4 superfluid. So I did not say Siri. Okay. Thankfully, she did not ask me a tough question. So that's it. So it's almost like a rule of nature that strongly interacting particles are combined to form weakly interacting particles of a new kind, which is very fortunate because as far as I know, the only things we understand nicely are things which can be described in terms of non-interacting particles. That's the only problem we can really solve. So even this question is not almost there. There's one more step. So let's ask, suppose we had some weakly interacting emergent particles. What would they have to do? Well, what can they do? The only thing they can do is show integer quantum Hall effect. So let me rephrase the question in the final form. Can we understand the fractional quantum Hall effect as the integral quantum Hall effect of certain emergent particles? Okay. In fact, we can arrive at this question from a different perspective. So we have seen this figure before, And one of the remarkable things about this figure is that it contains both the integer and the fractional quantum Hall effect. In fact, if I erase the numbers here and challenge you to tell me which plateaus correspond to integers and which correspond to fractions, it's not easy to tell. In fact, they all occur exactly in the same fashion. Plateau, 0, okay? So these phenomena are qualitatively identical, which indicates that there has to be a deep connection between them. So can we unify the integer and the fractional Hall effects? So this was something that had bothered me for a few years, but I didn't know what to do with it. So remember, I had the statement that the art is to ask the right question at the right time. The time also has to be right. So for example, to give you a beautiful example of this, superconductivity was discovered in 1911. And Einstein was at his prime at that time. There's no way he could have solved the problem. Because now we know in hindsight, you had to know quantum mechanics, you had to know Fermi statistics, you had to know Fermi liquid theory, you had to know electron-phonon interaction. Without those, you cannot solve the problem, no matter how smart you are. So one has to keep asking this question because you never know beforehand when you would be able to solve it. So in this case, when I was a postdoc in 1988, the answer suddenly occurred to me. But let me first acknowledge intellectual debt to lots of beautiful theoretical ideas that had come up in 1980s, which I have listed here, and of course, lots of really incredible experiments, which played a role in this thinking. So the idea was, and in fact, my wife still remembers, I was reading this book by Prange and Garvin. While the TV was on, I was doodling, and I told her, I think I had an important idea. So the idea was this. Okay, this is the only slide that will do this. Okay. So the idea was, I realized that if I assume the formation of certain kind of particles, then suddenly everything fit together. So this is a composite fermion. A composite fermion is defined as the bound state of an electron and an even number of quantized vortices. It's shown pictorially, and it's okay to think of it this way. It's okay to think of it as the bound state of an electron and an even number of magnetic flux quanta, where the flux quantum is defined here. Why can we do this? Because a quantized vortex and a magnetic flux quantum both share this topological property that a closed loop around either one of them gives you a phase of precisely 2 pi. And it's topological because the phase does not depend upon what path you take, so long as you're going around the vortex or the flux quantum. So I'm going to show you, so all of the theory can be summarized on 2 slides. So this is the intuitive picture. So this is what experimentalists need to know. So the postulate is that strongly interacting electrons at some magnetic field B transform into weakly interacting composite fermions like this. So here, each electron captures 2 or 4 or 6 flux quanta, and the flux can point up or down. And these composite fermions are then weakly interacting. That's the postulate. The most important thing we need to know is that the composite fermions now see a magnetic field, which is the leftover magnetic field. So the magnetic field that they have captured is now invisible to them. So composite fermions now form their own lambda-like levels. These are called lambda levels. And just like we did for electrons, we can calculate their filling factor. I call that nu CF. And we can derive this relationship, the relationship between nu and nu CF from this equation. So these two formulas, I mean, these are the same, but these can be derived from this. Okay? So BCF, just by looking at these pictures, you know, it's external field minus 2m flux quanta removed per electron. Rho is the electron density. So that's the composite fermion theory. Okay. We can actually go ahead and do more. So one way to deal with the problem is to say, okay, if there are composite fermions, does it suggest some wave functions? And the answer is yes. So I have mapped the problem of strongly interacting electrons to a weakly interacting electron problem. So I write the wave functions of weakly interacting electrons or non-interacting electrons at filling factor nu CF. I know ground state, excited states, you know, I can order them and label them by alpha. Then I multiply by this factor where Z is the position of the electron in 2 dimensions expressed in terms of this complex number. And we multiply by this Jasto factor. So this precisely has the effect of attaching 2m quantized vortices. Because as you know, Z1 minus Z2 has the property that as Z2 goes around Z1, you get a phase of 2 pi. So this converts all electrons into composite fermions. Now, there is one minor problem with this wave function that it's not at the lowest lambda level, and I would like to get a solution in the lowest lambda level. So I, by hand, project this into the lowest lambda level and identify this as the wave functions of fully interacting electrons at filling factor nu. Okay? So that's the wave function. Now, you notice that we started out with a problem where we had no idea where to begin in terms of electrons. Now here I write a single equation that provides ansatz wave functions for all eigenstates at all filling factors. You give me any filling factor nu, I can write wave functions for ground and excited states. And even more remarkably, when nu CF is an integer, this wave function is unique for the ground state. Remember, so for integer fillings, it's unique. And so therefore, this is the magic of composite fermions. So in terms of electrons, we had gazillion states. As soon as you look at the problem through composite fermions, it gives you one state. Okay. Let me skip that. There is another way to theorize composite fermions, which is through a theory called Chern-Simons field theory. And I just want to mention this because I think there are other fields like string theory where they also talk about Chern-Simons theory. And I don't know, I think there are some beautiful connections here, which I don't have the capability to see, but maybe some of you will. Okay. So I won't do anything more with this except mention it. All right, so Horst Stormer, he asked the question, how real are composite fermions? Do they exist? If so, in what sense do they behave as particles? Now, we theorists, we often fall in love with our theories. You know, we say, okay, this is so compelling, it's gotta be correct. But at the end of the day, experiments have the final word. You know, a theory has to explain experiments. So let's ask what composite fermion theory explains or predicts. And what I will tell you is that it explains thousands of facts in a supremely unified fashion. And, you know, so I cannot go over thousands of facts, but I will, they belong to certain classes okay, certain categories. So let's see what they are. So first thing they explain or they uncover is the origin of the fractional quantum Hall effect. So if you consider this filling factor of electrons, then ask what is the composite fermion filling factor, you find that it's an integer. So as I said, at these filling factors, when we look at the problem in terms of composite fermions, we get unique ground states with gaps. So the state at 1/3 can be represented like this. It's one filled level of composite fermions. This is the state at 2/5, ground state. This is at 3/7. And so this is what you would get if you assume composite fermions are non-interacting. And then you say, well, if you switch on the residual interaction between composite fermions, it won't immediately kill the gap. So it's possible that this gap would survive and you would see these fractions. The second success of composite fermion theory is that it explains the observed fractions. So if you look at these fractions, 1/3, 2/5, 3/7, and so on, these precisely follow the sequence P over 2P plus minus 1. Similarly, the fractions here, they follow the sequence P over 4P plus minus 1. So this is exactly what the composite fermion theory predicts. In fact, we say the fractional Hall effect is like the integer Hall effect. So let's just compare. So let me take this figure and plot it as a function of BCF. Okay, so remember BCF is equal to B minus something. I will take this figure and move it leftward so that BCF is 0 here. And then you notice that 1/3, 2/5, 3/7, 4/9, they align with 1, 2, 3, 4, 5. Okay, so it just looks like the integer Hall effect. In fact, these guys would look like the integer Hall effect of composite fermions with 4 flux quanta attached. You have to just move the upper panel further leftward. So the fractional quantum Hall effect at these filling factors is nothing but the integer quantum Hall effect of composite fermions. In this figure, we see composite fermions carrying 2 flux quanta in this region, 4 in this region, and composite fermions carrying 0 flux quanta in this region. What are composite fermions carrying 0 flux quanta? Louder? Electrons, thank you. Electrons are a special case of composite fermions. Experiments have shown evidence for states at, generated by composite fermions carrying 6 flux quanta and also 8 flux quanta. Excuse me. Many fractions along a given sequence are seen. In fact, in the best quality samples, this is so far the best quality sample. They see 14 members of this sequence and 16 of this sequence. Okay. The same fractions are seen in monolayer graphene. So these are fractions that correspond to P over 2P plus minus 1. These correspond to P over 4P plus minus 1. This is bilayer graphene, again, the same fractions. So the conclusion of this part is that the composite fermion theory correctly predicts the prominently observed fractions. And also it predicts that they appear in sequences, okay, because they all come from the sequence of integers. It also explains why the prominently observed fractions have odd denominators. Notice that we produce all fractions in one shot, okay? So all fractions are unified, but moreover, fractional and the integer Hall effects are unified. And the beauty is that so far you don't need any microscopic theory. Okay, the simple picture, you already get the result. Another important development, yes, please.
So when you map it, are the other details like the widths and so on, do they also map in some?
The width of the plateau.
Yeah.
Okay, that's indeed true. Okay, so so what in fact, I mean, this was shown earlier, but Avik Bid has a paper recently where he has measured it more precisely. So for integer Hall effect, if you say my disorder is particle hole symmetric, then the plateau would go from 0.5 to 1.5, 1.5 to 2.5. So what you do is from 1/3 to 2/5, you can calculate where the fractional plateaus would go. So the peak occurs at 1.5. You can ask at what. So we know in terms of composite fermions where how wide the plateaus are. You can translate that into what you would get for fractional Hall effect, and just works good. So we know. Okay. Any other questions? Yes, please.
So we know for superconductivity the idea of a Cooper pair and the fact that it exists was very fundamental actually. Now in this idea of a composite fermion, which sort of is some sort of a bound state, an electron with magnetic fluxes, is there some calculation that tells you that such a bound state exists really? Or
okay, so please wait for a little while. Okay, we'll see. So I should say in the case of superconductors, we can do some sort of mean field theory to derive it. Because superconductivity, although it's non-perturbative, but it's almost perturbative. Okay, so if you take a weakly coupled superconductor and look at it from afar, there is a Fermi sea. I mean, some little bit of rearrangement occurs near the Fermi energy. So there you have the luxury of starting with the Fermi sea wave function and doing perturbation theory, put in a little bit of, so it's a much simpler problem than fractional Hall effect. Okay, I'm saying it in hindsight, but that's my view. In fractional Hall effect, we don't have, so I cannot derive the wave function that I showed you, but we'll see that they do describe the reality. So just wait for a few minutes and the question will be answered. If not, please ask again. Okay, so there is a new phase of composite fermions, which is called a composite fermion metal. So let's subject the theory to a stress test by pushing it into a limit. So, for example, Einstein's theory of general relativity, if you push it to a limit, it gives you a black hole solution. You say it cannot happen, theory has to be wrong, but then it happens, so then you say, wow, okay. So here, let's push it to a limit where P goes to infinity. So that takes us to filling factor of electron equal to 1/2, half-filled lambda level. No fractional quantum Hall effect is seen at half, which was also a puzzle. You say this is the simplest fraction. How come there is no plateau at half? Well, if you look at the problem in terms of composite fermions, you notice that composite fermions eat up all of the magnetic field. So we end up with composite fermions in zero magnetic field. What do they do there? I mean, now they cannot make integer Hall effect. They form a Fermi sea, they form a metal. So that was the prediction of Halperin, Lee, and Reed. I mean, let me just point out that, remind you that the original problem had no kinetic energy. And things like Fermi sea or a lambda level, these are concepts related to the kinetic energy. It's rather surprising that we see these things here. without composite fermions, there's no way you would think of a Fermi sea here, okay? But Fermi sea is something that condensed matter physicists know how to deal with. So there has been like hundreds of experiments that have tested it. So first of all, a metal has no gap, and that's why there is no fractional Hall effect here. They have seen Shubnikov-de Haas oscillations. The Fermi wave vector has been measured. In fact, it just, okay, I mean, the surprising thing about it is that it behaves so much like an ordinary Fermi liquid that that's a surprising thing. So in fact, we are trying to look for non-Fermi liquid types signature, and we fail to find it. It just looks like a regular Fermi liquid. So lots and lots of different experiments have been done, which completely confirm a metallic state of composite fermions. So in fact, composite fermions unify even fractional and non-fractional Hall states. So composite fermions are more general than the fractional Hall effect. They apply to systems where there is no fractional Hall. Okay. Now let me come to the question that Quanta asked. Let's try to get a microscopic validation. So I'm going to show you results from two calculations. One is I will put, not I mean, this is done by my wonderful students. I could never do these calculations, but that's the advantage of having brilliant students. So we'll calculate the exact spectrum by brute force diagonalization of the Coulomb interaction. That's one calculation, no adjustable parameters. You get whatever result you get. The other is I will calculate the spectrum from these wave functions. Again, no approximations. In fact, these wave functions look simple, but when you want to put them on the computer, it's pretty complicated. It took us many, many years to learn how to do calculations with them. But now we can calculate for like hundreds of particles. Okay, so I'm going to take these two results and put them on the same plot. Okay, so let's see what we get. So this is an example. Filling factor 3/7. The calculation is done for a geometry that's called the spherical geometry. So you take your two-dimensional electron gas and wrap it onto the surface of a sphere. And the magnetic field now points radially outward. So it's just a choice of boundary conditions. It's a nice choice. In this case, the natural quantum number is the total orbital angular momentum. Okay, so that's the L here. What I have put here on top is the total number of independent basis functions. So at this angular momentum, there is 2.3 million basis functions. So for example, if you just want to write this one state, you need 2.3 million numbers. These are coefficients of the basis function. So this is showing the extremely low energy part of the Hilbert space. Let me also remind you that all of the structure, you see some gaps opening here and here and here. This is all coming from Coulomb interaction. If you switch off the interaction, all of these states would collapse into one energy, which is 0. Okay? What does composite fermion theory say? Well, it says this state should be thought of as this cartoon, but there is a precise wave function associated with this. So I write the wave function of 3 filled lambda levels of electrons, composite fermionize, project. Okay, so we know how to do this. These you say, okay, it's an exciton of composite fermions. So I create a particle-hole pair. Again, I know the wave function precisely. And it turns out that if you fix the angular momentum, you have a unique wave function. So before going further, we can ask, well, what are the quantum numbers allowed? And they match precisely with the quantum numbers seen here in exact diagonalization study. Then we say, okay, let's calculate the expectation value of the Coulomb interaction for this and these states, and you get the dots here. So notice this is this lot of spectrum up there. You get almost the right state. In fact, there is no reason to expect why it should work so well. So people ask me, most recently, I was at a birthday festival of Steve Kivelson, and Senthil, who is at MIT, he was asking me, why do these wave functions work so well? I don't know, but I'm happy they do. It kind of was shocking to us, but now we are used to this. So this is like an example of cracking the code. So let me, so suppose you do exact diagonalization for this, you have a bunch of numbers. That's what the computer gives you. You can keep looking at it forever and you have no idea what that means. Okay, these numbers have no meaning. I say, well, this is the meaning. So we can write this state in this form, and then I can see that vortices are bound to electrons. So there are composite fermions in there. In fact, initially you are very impressed how good the agreement is, but at some point you say, well, oh, there is a little bit of a difference. What can I do about that? You say there are also these higher energy bands. Well, what we can do, so here I have taken states with 0 kinetic energy, 1 kinetic energy. Let me also add 2 kinetic energy and diagonalize my Coulomb interaction within this basis. And I can explain this. And now you notice that these become all exact, okay? So we can improve the agreement to as many significant figures as we would like. A quasi-hole is a missing composite fermion. A quasi-particle is an additional composite fermion. Here I am showing you the density profile, 2 density profiles. One is calculated from composite fermion theory, the other is from exact diagonalization. And you cannot see 2 curves. It looks like there is only 1 curve because they fall exactly on top of each other. So far it's 3 7s, but I can take any filling factor. So this is what I get for 1/3, 2/5, in between, so I don't have to do exact diagonalization. I can take composite fermion theory and tell you what's happening. So miraculously, the infinite choices of the electron problem disappear when we view it in terms of the composite fermions. A single equation gives all low energy eigenstates at arbitrary filling factors in the lowest lambda level. Okay, and so Spenta, this is like a confirmation of these wave functions. I cannot derive the wave functions, but they are motivated by a well-defined physical idea. And you compare and they're almost exact. In fact, such comparison does not exist for any superconducting state. So Horst Stormer, who had asked the question, how real are composite fermion? He said after some of these developments, they're as real as Cooper pairs. So the summary so far is we understand these as integers. And by analogy, we understand these fractions as integers of composite fermions. And at filling factor 1/2, this is half fill lambda level, I have a Fermi sea of composite fermions. So in the title of my talk, I had said bizarre particles. So what are those? So we have talked about composite fermions so far, but there's another class of bizarre particles which are called anyons. So how many of you have heard of anyons? Okay, some, but not all. So you know, bosons and fermions have this property that if you exchange two of them, you get either a sign of +1 or -1. It turns out that in 2 dimensions, as you exchange 2 particles, there are more possibilities. So you can actually get a phase factor. So that's a generalization of the concept of bosons and fermions. And since this can be any statistics, they're called anyons. So it's a clever name given by Frank Wilczek. The concept first was proposed just from pure thought by 2 Norwegian physicists, Mørheim and Lidorch and Mørheim. And in fact, it was proposed just in late 1970s. And within a few years, fractional quantum Hall effect appeared, which seemed to provide a realization of this. So I'm giving this result without proof that if you take 2 quasi-particles shown like this, it gives you a phase factor here. So these quasi-particles or quasi-holes are anyons. And although the theorists have believed it for a long time, but in the last 3-4 years, experiments have finally seen evidence for fractional statistics, which has created a lot of excitement in the field. So now you start thinking in terms of composite fermions. So it gives you a new paradigm to look at the problem in, and you find that there are lots of. So you basically open your Ashcroft and Mermin and ask, and look at all the things that electrons do and ask, do composite fermions also do that? And they actually do most of those things. So they form, I already talked about integer quantum Hall effect, metallic state. I will say a few words about superconductors of composite fermions. So this complicated object, they can also pair. They show fractional Hall effect. They have bilayer states, stripes, crystals. And one can study lots of different properties of all of these different states. So let me just very quickly tell you about a few of those. If you want to learn about others, there are several books with nice chapters that you can look at. Okay, earlier I said, let's assume that the magnetic field is so high that the system is fully spin polarized. It turns out that experimentally, that's not always the case. You can, Z-band energy is not so large all the time. So the composite fermion theory actually predicts what are the possible spin polarizations of the ground state. Just to give an example, let's say if I take filling factor 4 dynes, that maps into filling 4 of composite fermions. This filling 4 could be all same spin or 3 lambda level with spin up, 1 with spin down, or 2 and 2. So this is spin singlet, this is partially polarized, this is fully polarized. And this is what they see experimentally. Moreover, we can theoretically make a prediction for what would be the Zeeman energy at which they would see transition from one state to another. So these circles here are theoretical predictions. So, we have spent a lot of time, too much time probably, trying to include all of the experimentally relevant effects, like finite width effects or lambda level mixing and so on, which make a correction to the prediction. So these circles are what theory predicts, and the stars are what experiment measures. This critical Zeeman energy is actually determined by very small Coulomb energy difference between the competing states. And we can calculate that within a few % accuracy. So we have also calculated theoretically the phase boundary phase diagram for Wigner solid and liquid. So this is theoretical prediction, and the experiment agrees beautifully with this. So for example, here the open symbols are liquid states as measured experimentally, the solid symbols are solids, regular solid. And you see here, it's liquid here, and it becomes solid here. So another new phase is a superconductor of composite fermions. So this, so I told you that the theory of non-interacting composite fermions gives only odd denominator fractions. It turns out experimentally many even denominator fractions have been seen. So what's happening there? Well, the picture is that here the composite fermion metal becomes unstable to a pairing of composite fermions because of the weak residual interaction between them. In fact, this is the second mechanism for fractional quantum Hall effect. So we had integer quantum Hall effect of composite fermions. That's one mechanism. Pairing of composite fermions is another. And let me just show you one example. So this is a calculation by a student, Anirban Sharma. So as a function of density and well width, quantum well width, he calculated that this region with blue dots is a metal. The region with red squares is a superconductor. And this is the experimental phase boundary. So it again works beautifully quantitatively. In fact, we also predicted that you can induce superconductivity by increasing lambda level mixing. So this kappa here, is a parameter that measures the strength of lambda level mixing, which means you bring lambda levels closer and closer to one another. And we made a prediction that at filling factor 1/4, at some point you would see a paired state, a fractional Hall state, and this is what they see experimentally. So there are lots of these states which have been seen experimentally, and we have predicted the nature of the pair. It's P wave, F wave, or you can have L equals -3. That's the angular momentum of the Cooper pair. So these have not been confirmed yet, but at least the prediction exists. The superconducting state has given another exotic particle. It's called the Majorana. So it's actually not the same Majorana as what Majorana had discovered. So he had discovered a real solution to Einstein equations. So Majorana particles are their own antiparticles. Sorry?
You said Einstein.
Thank you. Sorry about that. Indeed. Dirac equation. So the Majorana, so as far as we know, there is no Majorana particle in nature, although neutrino perhaps there is some possibility that it could be Majorana. In fractional Hall effect, we think of Majorana as a non-abelian. So the vortices of this superconductor have 0 energy states which capture half of a composite fermion. And this particle has the property that the creation operator is equal to the annihilation operator. These are not fermions actually. So Majorana fermion is a misnomer. You have to call it Majorana particle. These obey non-abelian statistics. And it's believed that they could be used for quantum computation. In fact, this idea has been taken fairly seriously by Microsoft. So they do not use Majoranas in fractional Hall states, but they attempt to create Majoranas in another system, which is in semiconductor nanowires, where Majoranas, if they occur, would be trapped at the ends. And recently there was this, they unveiled a Majorana 1 chip. Okay, so they have spent like $1 billion on this already. This proposal is not confirmed. It's not believed by everyone, but at least it's something, let's see what happens. And let me just mention one more thing before I call it a day. Very recently, something rather remarkable happened. So if you had told me 5 years ago, look, they will see fractional Hall effect is zero magnetic field, I would say no way, impossible. But fractional Hall effect has been seen in zero magnetic field in systems which are twisted bilayers of certain semiconductors. And they have also been seen in pentalayer graphene. And the fractions they see are again those predicted by the composite fermion theory. They have also seen evidence for metallic state of composite fermions at half filling. So when this happened, so I mentioned Stormer a couple of times. He happily retired from physics at the ripe old age of 59. So a lot of us could not believe it. We said, Horst, you are going to come back into physics, but he has not. So that was about 15 years ago. I could not resist. I sent him an email saying, Horst, I know you have retired from physics, but it may interest you to know that the fractional Hall effect has been seen in zero magnetic field. He said, absolutely mind-boggling, weirder than we ever thought. And I think that kind of applies to the whole field of fractional quantum Hall effect. This is the summary slide. Let me just say I have two dreams. One is composite fermions are harnessed for some technology. It could happen, for example, through Majorana particles or God knows what. But I think I would love for the structures revealed in the study of composite fermions or fractional quantum Hall effect to provide a crucial clue to some other problem in physics. So just like Higgs mechanism, which was discovered in superconductivity first, played an important role in the understanding of the standard model. Okay, so as I said, a lot of my students have made very important contributions here. I list, so I would like to thank all of them, and I thank you for your attention.
Thank you, Jainendra, for that very insightful lecture, taking us through all the history and the twists and turns, and a very fascinating story, which I think you managed to communicate to a large audience. So we'll take some questions.
So since Cooper pairs of composite fermions are formed, so is it that the residual interaction is attractive between composite fermions?
Yeah, so when electrons turn into composite fermions, we can treat composite fermions as weakly interacting, but sometimes the interaction can be weakly attractive. And the reason for that is kind of interesting. So when you form a composite fermion, you can attach two vortices. You cannot change that continuously. You have to attach two. That screens the interaction between electrons, which is what gives rise to weakly interacting particles. But sometimes it may overscreen. So, so what happens is, I showed you two results. One was Landau level mixing. So what Landau level mixing does is it reduces the strength of the interaction between electrons. It remains repulsive all the time, but at some point the interaction between composite fermions becomes attractive. And similarly with quantum well width, as you make the quantum well wider, the strength of the interaction between electrons becomes weaker. It remains repulsive all the time, but at some point, composite fermions become attractively interacting. And that's what causes this pairing transition between composites. So, I cannot give you a simple formula for the interaction between composite fermions in terms of the interaction between electrons, but that's something we can calculate with some hardware.
Hi, here. Yeah, as you said, once you put electrons in a large magnetic field, they'll prefer like capturing us in some of the magnetic quanta to form these composite fermions with either 2 quanta or 4 quanta or 6. But why not a mixture of them? Like if you're allowing electrons to have discrete quanta of magnetic flux attached to them and treat that as a new particle, why not a mixture of all these 2, 4, 6,
Yeah,
and
so-
that forming some sort of a Hall system?
Yeah, you can have that too.
Okay.
So a simple example of that is, let's say you have filling factor 1 plus half, 3 halves. Now, what would happen is the one filled lambda level it already has a gap, so it's kind of deep underneath. You cannot do much, so it remains electrons. The electrons in the second lambda level, they capture vortices to become composite fermions. So this is an example where the state is a mixture of electrons and CF2s, but you can composite fermionize this state and you get some state which has mixture of composite fermions carrying 2 flux quanta and composite fermions carrying 4 flux quanta. And such states have been seen,
Okay.
Of course, at the end of the day, you have to antisymmetrize the whole thing, but the interpretation is precisely what is.
So I had a similar question actually. So could you then think of sort of this as a fractional quantum Hall effect of the composite fermions themselves,
Exactly.
which would be kind of an integer quantum Hall effect of a composite fermion? Yeah.
Yes, you can. Yeah.
Mm. So good.
So again, in superconductivity, because of the Cooper pairing,
Yeah.
we usually write down a phenomenological field, which is a charged field of twice the electron charge. And you have this phenomenological Lagrangian, which Landau-Ginzburg type of theory. Do you have something like that possibly in for the case of composite fermions?
So you can, okay, so so there are two ways to do this. Okay, one is to write the BCS wave function. And once you have the BCS wave function, there is some adjustable parameters which are like gap, so there's UK, VK. You ask for a given interaction, you minimize the energy with respect to these parameters. And if the gap is non-zero, you say it's superconducting. If the gap is zero, it's not. For composite fermions, you can write the BCS wave function, but it's not easy to calculate the expectation value of the interaction, precisely for the reasons that I had mentioned earlier, because there you can work with electron operators. Here we don't have those at our disposal. So the calculation I had mentioned, the work is done numerically. So numerically, one calculates what parameters give you the lowest energy. And if the gap function is non-zero, you put red square. If the gap function is zero, you put blue dot. Now, the second part of the question is some Landau-Ginzburg theory. I suspect one can write that. At some level, just the theory that we had for electrons with some adjustable parameters like the mass of composite fermions and so on would do a pretty good job. So, so these superconductors I described, they are like, their order parameter is px plus ipy. So they are p wave, but they are more than p wave, px plus ipy. They have Majoranas, but even electron superconductors, which have order parameter px plus ipy, would have Majoranas. So at a qualitative level, you can just use the same Lagrangian to describe these.
Is it, in fact, like this Chern-Simons description that you said, perhaps the analog of that?
Chern-Simons is not about pairing, it's about composite fermions.
Exactly. No,
Yeah.
I meant, because like Spencer was asking for an analog of an effective field theory for the composite fermions.
So for composite fermions, the effective field theory would be the Chern-Simons theory, where the Chern-Simons transformation precisely attaches even number of flux quanta to each electron. Yeah,
No.
not in terms of no, electrons bound to gauge fields. I mean, these vortices are like gauge. So it precisely, yeah.
Yeah, but those would be the anionic, those are these anionic things. I guess that's the closest you can probably write local kind of a theory, probably, because.
I mean, I should say that if you write that Chern-Simons field theory and you honestly do calculations, you don't get the correct answers for quantities which are non-universal. For example, the gap. So you cannot get rid of the electron mass. Okay, you cannot do any lowest lambda level projection in those theories. So there is a sleight of hand. You say at some point you replace electron mass by m star, and you say, okay, I would think of it as composite fermion mass, and then it works reasonably well, but it's an open problem in my mind. Okay, we don't have a satisfactory answer to that question yet.
Up there, yeah. No, it's.
Yeah, so I am not a condensed matter physicist. So I just had one question that integer quantum Hall effect is so well understood, like, I mean, like the Chern number term, also the age state, etc. So I'm asking, like, historically, like when you proposed it, what was the reaction? Like, I mean, of course, it phenomenologically fits with very well, but was there some resistance because there is no microscopic theory as such, as you said, also like the age state of integer was so if you can little bit walk down with when you published this PRL paper, what was the reaction? Like whether the lack of microscopic theory or etc. was a little bit resistance or what? So that's what I was wondering.
Is the talk being recorded?
Huh?
Okay. So this was not believed by lots of people.
Yeah.
Okay. So in fact, at the time of my tenure, the person who was chair of the committee was saying they went and looked at the citations. Okay, so in those days you had to actually go to the library, and there were these packed books. You could not find it on the computer easily. He said for first 3-4 years it had no citations except my own citations, but then it took off. So initially people did not believe it. In fact, I was attacked by well-known people, so I can tell you the story later on. But so at that time it was frustrating for me, but now I think that was a good thing because I had to work harder and, think about many, many more manifestations of composite fermions. So it forced me to improve the theory. Okay, so I think that was a good thing.
Thank you very much.
Okay.
And I should say that's the way it should happen. So any new concept, should not be accepted immediately. You have to be as critical as possible, right?
Thank you very much, sir. Real honor.
Okay, I don't see any more questions. So let's thank Jainendra again for a very inspiring talk.